To your distance learning lessons on thermal physics. Today we are looking at the kinetic energy of gas molecules. This is actually the last lesson in the thermal physics part of the course, so well done on making it this far through. We will revisit all of this when we get back to school, so do not worry if there is something that you felt that you didn't quite understand. Let's get started then. As usual, we'll start with a knowledge retrieval, so pause this screen and take 3 minutes to try and answer the following 3 questions. Right, let's mark these answers then. Question 1 asked you to list 2 assumptions that we must make about an ideal gas when we are thinking about kinetic theory. So you could have had any 2 from the Rayleigh mnemonic from last lesson. That is that we've got random motions of all particles, there is no attraction between the particles, volume of the particle themselves is negligible compared to the volume of the container, collisions are all elastic, so therefore kinetic energy is conserved, and the fact that we've got the distribution of particles, the time between particles, the time between collisions is much greater than the collisions of the particles themselves. Question 2 asks, what does CRMS represent? That is the root mean square speed, and this time we're talking about the molecules in a gas, so it's the square root of the mean of the squared speeds of the molecules. And question 3 asked you to give 2 reasons why increasing the temperature of gas increases the force it exerts on the walls of the container. So back in GCSE, you probably would have said something like increasing the temperature increases the kinetic energy, and therefore they're moving faster, and therefore they're more likely to collide with the wall. We now need to move away from that description and start thinking about the momentum of the particles instead. So last time, and in fact gearing up to last lesson, we were looking at the average change in momentum, and this time it's increased, and therefore the average time between collisions is reduced, and that means that the rate of change of momentum is greater, and because that is proportional to force, the force is therefore greater. We want to look and explore the kinetic energy of the gas molecules that we have within our containers. Kinetic energy, as you know, is all about the energy in moving particles, and obviously for gas we have an awful lot of moving particles. It would be really silly of us to work out the individual kinetic energies of every single particle in a body of gas, but we can find the average and total kinetic energy quite easily. So because we're dealing with ideal gases, we're just going to assume that all the internal energy is in the form of kinetic energy. If we assume that, then we can use our ideal gas equation to find the average and the total kinetic energy. So, 2 equations that we want to think about here. First of all, we've got our ideal gas equation, which was the fact that PV is equal to nRT. So that's equation 1. And we've got equation 2, which is from our kinetic theory, which we did last lesson. So PV is equal to 1/3 nmCRMS squared. There are 2 equations. Now, obviously, they're both equal to PV, so we're going to equate them. If we equate 1 and 2, then we're going to get 1/3 nmCRMS squared is equal to nRT. Now, we know that the kinetic energy is normally equal to 1/2 mv squared. So we want to try and put our equation that we've got here into a form like our normal kinetic energy equation. Now you can see that we've got a speed squared, we've got a mass, we've got this pesky little n here, and we've got everything in terms of a third. So we're almost there, but we want to kind of get rid of that 1/3. So what we're going to do, because to get rid of the 1/3, we're going to multiply both sides of our equation by 3/2. So if we do that, we're getting 3/2 times by 1/3 nm CRMS squared is equal to 3, oops, that's an N, RT over 2. Once we cancel all that, or work out what we've got on the left-hand side, sorry, we're left with 1/2 nm CM S squared is equal to this. And we want to get rid of the n from that side of the equation, so we're going to take it over to the other side. Therefore, we end up with something that resembles our kinetic energy equation. Like so. So here we've got our average kinetic energy of the gas molecules. And that's obviously measured in joules as per. N, as usual, is our number of moles of gas. R, sorry, that's little n, okay, so that's the number of moles. R is our molar gas constant, T is the temperature of the gas in Kelvin, and big N is the number of molecules of gas. So we have our equation for kinetic energy. But it's a bit clunky. So what we want to do is we want to recall that instead of using PV equals nRT, we could have also used PV equals nKT. So we're going to substitute nk for nr in our equation. If we do that, on the right hand side, we end up with, you can see that the n's will cancel and we're left with the average kinetic energy of the molecules in any substance is equal to 3/2 kT. Now, on top of that, we can recall that the Boltzmann's constant, K, is equal to R over NA. So we could substitute as well this into the equation here, and we can also find that the total, or we can use this to find the total average kinetic energy, equal to 3/2 RT over NA. So we use this formula to find the average kinetic energy of a molecule, and we use this formula to find the average kinetic energy total. Let's have a look at some examples to see what I actually mean here. So, first example, what is the average kinetic energy of the molecules in an ideal gas at 100 degrees C? So we're just going to put these numbers straight into our new equation that we have learned for kinetic energy. So that is that kinetic energy, or 1/2 mCMRS squared, is equal to 3/2 kT. If we put the numbers in, 3/2 times Boltzmann's constant, which is 1.38 times 10 to the minus 23, multiplied by 100 plus 273, because remember we want it in the Kelvin scale rather than degrees C scale. If we plug those numbers into our calculator, 7.72 times 10 to the minus 21 joules is our answer. Straightforward. Next example. What is the total kinetic energy of 3 moles of an ideal gas at 341 Kelvin? So, first of all, I want to find out the average kinetic energy of the molecules. I'm going to do that by using our other version of the equation, and that is that kinetic energy is equal to 3/2 times R times temperature times Avogadro's number. Plug the numbers in. This time we've got our temperature in Kelvin scale, so we don't have to worry about changing that. Remember that Avogadro's number is 6.02 times 10 to the 23. We'll end up with our average kinetic energy of 7.06 times 10 to the minus 21 joules. We're then going to multiply that by the number of molecules in the gas. So, remember that number of moles times Avogadro's number times our energy that we've just found out, which was 7.06 times 10 to the 21. And that is because that's going to give us big N. We're going to do 3 times by 6.02 times 10 to the 23 times by 7.06 times 10 to the minus 21, and we'll end up with 12,800 joules of energy in total of 3 moles of an ideal gas. And that makes sense. We've got a really small amount of energy for one single particle, but you know that in any sort of amount of gas, there's going to be way, way more than just one single particle. So we need to multiply them by the number of particles in that amount of molar substance by the energy that we've just found out to get our total kinetic energy, which is quite high because we have a lot of particles within that gas. So that concludes basically our thermal physics topic. We're going to do a little bit of a research topic on the development of the theories that we've been looking at on Wednesday, and then I'm going to set you a booklet that I've been working on that I think will be quite helpful in terms of your revision and understanding of this topic, and then we'll see how we go on from there.